So I'm recording the session right now. Can you see my screen right now?
Yes.
And I'm audible, yes? My voice is clear and
Yes.
everything, because we record it and we need everything to be clear for to be referenced for other students. So, okay. I have only one USB portal, so yeah. So I mean, it was the camera right now to present. So let's start. I think we need to assume that actually this is a meeting, not a lecture. But I tried to share with you, and actually I suppose that no one of us know anything about photonics. So I actually get a brief about what is photonics, how can we simulate our photonic devices, etc. So I will touch upon the headlines in this very quickly, but actually, before share with you the objective of this meeting, as I think I need to each one of us get acquainted with each other. So if everyone can share with you the experience, the expectation from this project, it will be so great. Marianka, how are you?
I'm good. I just returned from my university. It's full traffic out there. Just 2 minutes, please. I'll get settled down.
No, nothing. I need to see you right now, so I will open my camera. No.
My camera is switched on. I don't know. My video is not coming.
Yes, great.
Is it coming? I don't think.
So I just said that we need to share our experience with each other too. So everyone, if need to introduce himself, actually to get acquainted with each other. I know there is an introduction meeting with Dr. Shafa 1 week in the first of this program, but I actually, if you want that, you can share with us your experience or the expectation of this project. Anyone? Zainab, for example, if you can share with you your expectation and.
Can you give me more clarification? Expectation value, like about concerning the project?
Yes, about the project at all, about the project, about all the project, about why.
What I expect.
Yes, expectation and.
All right. If I get if I really understand the point of view of the project, that we will try to design like a photonic system and simulate it classically, and then we will have like numerical data, and this numerical data we will try to train it using classical machine learning model and compare it to quantum machine learning model.
Yes, that's great. Yes, that's great. But
so I think the difficult point and the necessary is the first one, is like getting like a high quality of photonic data in first, and then it is easy like to use models and train data. So the first step is like find appropriate photonic system that may be proposed like a quantum sensor for biologic system, for biologic application, and then simulate it classically, maybe using some like you mentioned this Cosmol software, I think, Mathematica.
Yes, that's a great.
Yeah. And then after we have data, we can train it to see the power of quantum computing compared to classical one.
Yes, that's a great. Yeah. I actually said that if do you know each other? Because it's first time for me to meet you. So I just wanted to introduce ourselves. The experience about what you want to learn. For example, I want to learn from you the quantum side, the quantum optimization and
Oh,
simulation, and I'm eager to learn that from all of you. Maybe I have some knowledge about the classical machine learning and photonics, of course. So actually, I'm here to learn from you. So I maybe I have some published 2 papers related to photonics, but I actually need to add this quantum perspective. So we need to share with us the experience, but maybe we can do that and at the end of the meeting if you want that.
Yeah.
okay, as you want.
I'd like to do that right now because we need to be
I
more
can
interactive.
go first. I can go first.
Yes, great.
Okay, so hello guys. My name is Muhammad Usaid, and so basically I have been working as a research engineer. So my experience is mostly I have worked with generative AI. I have worked with GANs. I have worked with like in classical machine learning, deep learning, etc. I am interested in quantum computing since like because I did a minor in physics, so I was always like interested in quantum computing and to explore how I can use my CS skills for like somehow merge it with like physics and so yeah, I did some courses. I have been involved with QWorld for like more than 2 years now. I have taken part in the last 2 Q intern programs as well, and I have like made a little bit of quantum machine learning as well, right? So basically, I think I can contribute like more in the machine learning side and maybe some part of quantum. And I am really looking forward to learn more about photonics because that's something that I really don't know too much about. So yeah, and unlike you guys, I haven't joined all the groups. So I only joined classical machine learning because I think that's because it creates confusion, right? So I know like what I have to work on, and then maybe I can learn from you guys, and it all works out at the end.
Great. Thank you, Muhammad. Thank you. Manijanka, do you want to share with us?
Definitely. You can hear me, I suppose.
Great, can hear you. Very well.
Yeah. I think I can contribute from the photonic side, electromagnetism. This is what I've learned in my master's years, and I'm really eager to work in this area. I want to know more about the machine learning part, actually, to be honest, the quantum machine learning, because right now I have attended a workshop on deep learning and machine learning. I think from the 100% of the workshop, I can acquire only 10% what GA and GAN, CNN, these are all are. And quantum machine learning will be much better for me. Because I've been dealing with quantum mechanics from my bachelor's days to master's days. The knowledge of linear algebra will help a lot in quantum machine learning. And photonics background, I've been working with photonic systems in my university days itself. So I have the knowledge of the electromagnetic theories and all things. I think it will help a lot.
Great. Actually, we are about to have an introduction, a brief about photonics. So I think your help will be very appreciated. This meeting.
Surely.
Actually, I believe that Muhammad Usaid will help you probably in the PS because his expertise in this field. Actually, Muhammad will help all of us.
Some revision. I need some revision in photonics. It will brush me up much better because it's been a year. I'm not dealing with that part. I need some brush ups.
That's great.
Okay.
Very happy to see you. I'm very happy to see Muhammad, of course. Anyone? Asma, how are you? Thank you, Asma. Asma has joined us right now, so I think maybe she.
I can go. I can say.
Yes, Pranshi. Great.
Hi. So my name is Pranshi, and I'm working in quantum machine learning from past 2 years now. So I'm working with Deloitte, and I joined this project because it's opposite to what Mrigank said, that I have experience in quantum machine learning, but I do want to learn, photonics and the hardware side of the quantum system, because nowadays in research in general, they are expecting everyone to have knowledge of, both the sides, hardware and software as well. So that is my expectation, and I can contribute to the quantum machine learning part and classical machine learning part as well. Yeah, in the project.
Great. So I think
may I say something?
Yeah,
To be honest, I think I will be the most junior most. I am just fresh to research. Please do help me with it. I'm very excited to work in related paper related works. No, I'm very fresh to research. I've done my dissertation from my university, but I think it will be a great opportunity for me. I'm very fresh to research area.
that's great. So, and actually we have Raja, he is a mentor of quantum team, quantum machine learning. Actually, he's a great man. So if you'd like to share with us, Raja, and we are really happy to have you in this meeting. Raja, can you hear us? Raja.
Hello, sir. Am I audible, right?
Yes. If you want to share, yeah.
So, I mean, so as I was saying that I don't have that much experience in this quantum machine learning field as of now, but I do have good hands-on experience in this classical machine learning and this quantum computing field, and along that little bit knowledge about this semiconductors also. So I do have knowledge of every field, not that much, but I can contribute in every field for now. And when it comes to quantum machine learning side, so I am actually working on it, and side by side with this project actually I can actually enhance it properly, because in college I don't have that much project which is related to this quantum machine learning field, but it was project related to proper quantum computing. So I do have good hands on this quantum computing. And when it comes to quantum machine learning, that I can easily not easily, but I can totally work in that field, because I have good hands on this classical machine learning side, so I can cooperate in that one.
Great, great. So, do you have any experience regarding photonic devices and how simulate photonic devices in any framework, like for example, numerical console or whatever?
Not yet actually, because actually I've already worked on this FPGA board actually in my master's program.
Yes, great.
Because
Because yeah. Go ahead.
So I only had experience in this FPGA board development. So it was a quantum key distribution product, one of which we have to make it. So in FPGA, I do have hands-on experience, but in photonics, I don't have that much. Though I have studied, it was a part of our course curriculum, but we didn't went into too depth actually in photonics sections.
Yes, great. I'm asking you because I noted that Mohammed, Branchi, and Zainab and you dear need to know more about photonics. Maybe we have Asma Magdi joined us right now. She is a master student in quantum photonics. Actually, I believe that she has a great experience in photonic device. So actually, I think that would be suitable to have at first a small presentation about the photonics, photonic devices, and how we simulate photonic devices in a nutshell. Are you accepting that? Can I share with you my screen to share this presentation or not?
Yes, of course.
Yes.
Surely.
Yeah.
And I want to add one more thing. I think most of us have engineering or electrical, electronics or / physics background.
Yes.
So even though we haven't studied worked on photonics, I think it will be easier for us to pick up the topics, because it's the higher version of what we have studied in college.
Yes, that's a great notice. Yeah. So I think we will move on this actually, because the content actually here is what is photonics and fundamental technologies, real life application in emerging fields. So I think the objective of this meeting actually is to be at the same ground, right? Like what Zainab said at the very beginning. What is the architecture of this project? We need to see the big picture of this project. All of us need to see the same picture from the same perspective at the first time. And so this is the starting point. We need to move forward, and of course, this architecture may be get more complicated with time. So the final thing that we need to set what the expected contribution from HT. I think that these are only the objectives that related to this meeting, but actually we can move on photonic device. For example, this is actually the architecture, simple architecture for us. Like Zainab said, we as a photonic team, we design the photonic device, then simulate, use console numeric or any other software package. Then we extract the data, or for example, some of papers provided by Dr. Safa. Actually, the data is available online, so we can work from the classical machine learning team point of view or quantum machine learning. They can use the available data to actually create their models, to apply the different models, and compare results from all of these actually model that they applied in their notebook. So actually, this assemble architecture of how can we interact with each other, how can we collaborate with each other, the rules from HT, and we will back into it. But before that, of course, photonics. What is photonics? I think most of you search about that. Actually, photonics is I like to define photonics as the science of the interaction of light and the radiant energy whose quantum unit is photon, and with the material. So the interaction of light with the material itself. But photonics actually is defined as a science of light to generate energy, detect or transmit information. So you may found a lot of definition, but this definition is the most generalized one. So fundamental technologies, of course, we can use it in imaging, laser lenses, machine vision. All of you know that. And of course, optical fibers, sensors. These two are the specific related to our project. So of course, if you see the video that I upload, actually I sent it to you via Discord. How can we imagine our life without photonics? Actually, in aerospace, for example, there is holographics. Holographics are employed in head-up displays. And of course, in communication, biology, and medicine, for example, to detect disease such as glaucoma, Alzheimer's disease, and whatever. Of course, consumer electronics, as you know, lighting, transportation, if you touch upon the automotive industry or whatever, and of course, agriculture, for example, because if you know something like light management enable hydroponic greenhouse projects, actually in which our food can be grown in hospital climates. So actually, photonics is everywhere. So I move fast and quickly on all of these topics because I believe that most of you or all of you can know about that. So if you need something, you can stop me and discuss about it. So the emerging fields, actually, I suppose that all of you can hear me clearly. Yes?
Loud and clear.
Yeah, thank you. Loud and clear. I'd like to lower my voice. Yeah. So in the emerging fields, like for example, quantum technology, because all of you know that quantum physics is another area of science that intersects with photonics, and our project is all about quantum technology and quantum computers. All of these fields are actually interoperable between each other, so we can interdisciplinary, because silicon photonics, of course, can be used in quantum computing, and actually maybe optogenetics is far away of this, but we can use quantum machine learning and classical machine learning, for example, in plasmonics. But before that, silicon photonics is already used today for every system-to-system connections in data centers. For example, AWS or Microsoft Azure or whatever. So in addition to that, optogenetics actually is the use of light to control cells and living tissue. And that lead to insights into neurological and psychiatric disorders, like, for example, autism, Parkinson's disease, and whatever. Actually, last but not least, plasmonics. Plasmonics is the subset of photonics that studies what's so-called plasmon. Do anyone know about plasmonics before you?
I do have a rough idea about it.
Yes, great. So I'm very happy, because actually I give that I will give the because if you can share with us your experience about plasmonics.
Yeah, in my master's days, in my last year, the second year, I was introduced to the plasmonics. It's all about light matter interaction in metal dielectric interface,
Great.
and it's all about those. And I have to brush up. I'm telling you, I need to brush up. I need to open those books and see what's there inside the equations and surface plasmon resonance, SPR. Those things occurs. I have been acquainted to all these words.
Yes,
That's it.
great. So to make it in a simple way for everyone, as it's the study of plasmon, and the plasmon is a quantum unit of plasma. So we can take the advantage of coupling of light to the charges as electron emitters, and this can lead to a potential applications, for example, to engineer a negative refractive index materials, metamaterials and whatever. So there is a lot of different ways to leverage machine learning models, classical or quantum, in this field. So photonic devices, we need to jump into our. I like to give you how photonic devices work. So, for example, optical waveguide or waveguide finite difference time domain simulation. I will share with you this video. If you can see this is like a simulation in numerical. This pulse from the laser pulse, and this, these two lines are called waveguide. So the light. This is a simulation of how the light propagates in this waveguide, and at this point, this ring cable, the light cable between the point of intersection between the ring and the waveguide, so something called a coupling, So if you know part of this wave propagate in this ring, the first ring and the second ring. This is how we can simulate the optical ring resonator in finite difference time domain simulation. So if you don't know about optical waveguide, what's basically optical waveguide that generate actually the light generate in this propagate actually in this.
A lot of communications are done, including telephone and other communications. You may have an optical cable in your home stereo or home theater system that communicates audio information through an optical cable. The principle is total internal reflection. If we come in at a glancing angle, then all of the light that's incident on this surface and on this surface will be reflected back internally into the material. So it works for glancing angles, and then the surrounding material. But any shape will do. You can use a rectangular shape here. You can use a circular light inside of that fiber.
Actually, assuming that you know this, but I'd like to only to say that the waveguide, the optical waveguide from the previous video, this is like this exactly, but in the nanoscale, and we use one wavelength, of course, from the laser. For example, the wavelength is about 1,550 or 1.55 micrometer, and this is like a standard, So actually, this total internal reflection principle is applied in the nanoscale waveguide. So I apply a laser in a silicon waveguide, and the total reflection phenomena occurred in the nanoscale. I'd like to link this video from with the previous one. So how can optoelectronic device work?
some electrical energy is supplied to the diode, due to which the electrons are released from the valence band and hence a hole is created in the band. Due to the flow of electrons, a current also starts flowing in the circuit. As more and more electrons start eliminating from the energy band, more and more current flows through the circuit.
So organic photovoltaics is actually like, it's actually a solar cell, you know? You know how the light interact with the material itself to generate electrons, you know? So that's why that's actually an optoelectronic device. But why I share with you this very simple videos, because you need to know that every device has its own parameters, of course. So for example, if we share the yes, this paper, all of our 3 papers, can you see it right now?
Yeah.
Yes, great. So for example, this paper had tried to simulate a nanosensor. So the parameters here from not this, like, yes, this. The parameters here is if you read this, yes, if you read this, you can find that this optical fiber photonic crystal fiber has its own parameters. For example, the D, the lambda, and the space between crystals and what is the perfect matching layer and whatever. So there is an input data you need to know, and the output. For example, the effective refractive index, that there is an input. So if I try to simulate this photonic device, I will generate data that you will feed it into your, for example, artificial neural network. So the type of data, for example, the optical parameters here is effective refractive index, the diameter, for example, and the mode and whatever. And this is the input data, and the output is what is a chromatic dispersion, what is a confinement loss. And actually, sorry, the effective refractive index is the output in the output layer. So the type of these data is different from, for example, optoelectronics device, the solar cell, the sensor. If I apply here the sensor, I apply it only to draw the wavelengths, or actually the incident angle versus the sensitivity, and the wavelengths versus sensitivity or the transmission. For example, here the incident angle. No. He studied the incident angle with the sensitivity, and the thickness of the effect layer with the sensitivity, and the wavelengths, temporal wavelengths with the sensitivity. So different, because here he care about the sensitivity, and the input is wavelengths, incident angle, and the thickness layer. So because this design is different, both of these designs has different parameters to study. So I actually want to say that every design has its own parameters to study, and its own parameter to apply to a machine learning model. So how can actually we simulate this these photonic devices? For example, we can use numerical package, and this numerical package you can use. Actually, it's a very popular software for photonic devices. We can simulate a solar cell, OLEDs, integrated optics, like you have said before, nanoparticles, plasmonics, echo crystals, and so on. So of course there is a lot of solved example in this software, and you can apply it by your own. Only you can download the file and generate the data, for example, via sweep analysis or whatever. Why we use numerical? You know, the same target, like why we use a machine learning model, because we need to save time, save cost, greater accuracy, and so on. And of course, we cannot go to manufacture process every time we have a new idea, you know, for example. So of course, simulation, and you know the difference between predictive and prescriptive, you know, because if I use for example, optical swarm optimization, I need to use a predictive model. A predictive model is actually any machine learning model plus the business case, the business scenario. So if I use Monte Carlo, if I use any swarm optimization, vertical swarm or whatever, you can reach the optimum parameter. But we can do the same with machine learning model, you know. So the first step is we use a different package from Numerical. Numerical is the main company, and actually is acquired right now by a company called ANSYS. There is a lot of solvers. For example, we can use finite different time domain solution, mode solution for the waveguide only design environment. So if you need to design photonic integrated circuit, so the mode solutions, actually this is an older version of numerical, but the mode solution will be the suitable package for you. Finite difference time domain, for example, if you need to simulate a nanowire for solar cell, or even anything related to the nanophotonic device in 2D and 3D, this package can do very well. I think the meeting will have less than 1 minute. So if actually I use my Ottawa University account, I don't know why they do that, but okay, if it's closed, I will send you another link via Discord. Okay.
Yeah, sure.
Yes.
Sure.
Okay. Okay. So actually, device is another package from numerical. If you need to design a system that can be photogenerated, for example, the solar cell have two characteristics from we need to maximize the efficiency to trap the light that coming from the sun. If we trap more photons, we can get more efficiency. So we need to simulate this in finite difference time domain solution.